So when we look at this this topic here, this portion here we deal with the drawing of magnetic field. So in a simple nutshell, you can see that when we talk about magnetic field, we are talking about those few lines over here. So from those few lines, we have you can see that from the direction, the magnetic field lines exit from north entering south. And also those that are nearer to the poles, they tend to be closer together. And those that are further away from the pole, they are far apart, indicating the strength. Because when they have higher concentration of the lines, it indicates a stronger field and vice versa. So do we need to draw something so complicated, right? Or so many lines? Not really. So in the exam, what we will do, a simple magnet that's normally acceptable. So do make sure that the lines point outwards from the north and going into the south pole, out of north into south. So first off, we will draw like two rings here. Make sure they don't overlap. And then we draw two more lines to indicate those that are something like this, that are far apart. And then we draw two more lines to the back. Make sure they don't overlap. Next, we fix in the arrowheads. They are all going out of north. And they are going into the magnets from the south side. Okay, this will be the easy way of drawing the magnetic field lines around the piece of magnet. So do take notes when they are strong. They are normally closer together. And it's always out of north into south. Okay, nothing much here. So the next portion, we have how magnetic field lines interact with each other. Is Sanjana home already? Or still on the way? We are doing the next portion here. Okay, so as you can see from here, magnetic field lines always exit the North Pole, entering the South Pole. So what happens when we put two pieces of magnet together? So when we place two pieces of magnet together, depending on the polarity. So if you look at this setup, it's always north going into south. So very easily the magnetic field lines actually transmit into the South Pole from this magnet to this magnet. And look at the arrowheads, it's always pointing out from the north. All the arrows point out from the north, always going into the South Pole. Okay, and similarly, the field has to go backwards, just like how we draw it over here. So magnetic field line always go from north to south. So we need to draw them this way, going from north to south when these two pieces interact. Similarly for this, when the field lines go from north to south, you can see that all the field lines going this way, the field line going this way, and coming out from north, going into south, out of north, into south, and this way from north to south, this way from north to south. So always orientate your magnetic field lines coming out from the North Pole, going into the South Pole. So this is when you have like poles together. What happens when you have unlike poles coming together? So so just now we have unlike poles, sorry. So now what happens we have like poles together. So we have like poles together, you will see that their magnetic field lines actually points out. For example, the two north pointing together, they all point out together. So the field cannot move from one pole to another, so to speak. The field lines doesn't really connect from north to south. So what happens is both of the magnetic field line from the north over here, you see that they push out from each other. And this results in producing this point X here, which is known as the neutral point, which in normal understanding, it means that this is actually just a region without magnetic field lines. Okay, so they will kind. So this actually, this kind of drawing, you will see that it actually leads to repulsion. And when the field lines actually can connect, this actually leads to an attraction. Okay, so same thing when you have south and south going to against each other. So your south and south going into each other, it is still the same. They're going to push away each other and you get a neutral point over there. So the field doesn't connect. So similarly, like this case, the field doesn't connect. They just do their own thing together. They just do their own thing, so to speak. Okay, so for this portion, it's just the field lines, how they interact with each other. Can I give you a minute to look through the field lines? Make sure you understand that field lines always move out of move out of the north, going out of the north, and always moving from north to south. Always exiting north, entering south. Okay, so can I give you a minute to check this out? Yeah, just to digest this a bit, then we move into plotting. Okay, please take a look first. Any question, please sound out. Okay, let's take a look. No questions for me? If not, I'll go on to the next point. But this is a plotting. We are trying to plot the magnetic field using a compass. So what do we mean by plotting using a compass? That means we are trying to trace out, right, the direction of the magnetic field using a normal compass. Okay, so let me draw this here. More, need a bit of space. Okay, first off, the concept. Okay, the needle of the compass will always follow direction of the magnetic field, always. So from our understanding, right, let's take a piece of magnet again. If we have north and south over here, so we have our magnetic field lines going out of north, going in towards the south pole. Similarly, the other side, going out of north and going into the south pole. And then we have this all these lines that represents like going far away. And behind going in. So with these few lines, what happens, right, when we actually place a compass near to them? What's going to happen to the compass needle when we place them around the piece of magnets with a significant magnetic field? Okay, as we say, the compass will actually follow the direction of the magnetic field. So all these ones you can see is pretty straightforward. It's going to follow the direction of the magnetic field. It's going to go this way. This is going to point like this. Okay, because these are the turning edges. This is coming out straight. This is going in straight. And this is going towards the South Pole. So you can see that when you place a piece of magnet near a magnetic field, it will align the compass needle in the same direction as your magnetic field. Okay, so how do we going to use this to help us plot the magnetic field out using a compass? So let's take a look at the plotting process. Okay, so let's say I have a piece of magnet over here, north and south. Okay, a piece of magnets will not have visible magnetic field lines. So this is the steps that we will take. So step one, we are going to place the compass at the North Pole. And then we're going to place a dot where the arrow of the needle of the compass. Okay, what do I mean by that? So we're going to place it here. This is first position. So we're going to put a compass and place a dot here. So the next thing that we're going to do is step number 2. So we're going to remove compass 1. Remove the compass. Actually, we only got one compass. So we're going to remove the compass. And then we are going to place the tail end of the needle at the dot. So what we meant is this. So place your compass here and then orientate it in such a way that the needle, the end of the needle touches here, touches the point. And then again, we're going to place a dot at the arrowhead of the needle, which means we're going to put one more spot here. So as you can see, step 3, we are going to repeat step 2. Remove the compass and then place a third one here. Same thing, the tail will align, then we put a dot over here. Let me do a quick save. If I lose this. Step 4. You can see this coming away. Repeat. Step 3. And so on until until we get a whole chain that duplicates all the way. Oops, the blue one. Place a dot here. And so on, right? So I'm just going to do a quick duplication. Something like this. Until we go one full round. Okay, my drawing not very nice, but this is the general idea. So once we do this, we know this is the general direction of the magnetic field. Okay, so after repeating all the steps so many times, right, the last step will be remove the compass, and then we will join up all the dots. So once you join all the dots, you know that's the path of the magnetic field that is taken. Then you can actually trace it out. This is how we will do it. Okay, this process is called over here, we call this process the plotting of the magnetic field using a compass. Okay. All right, Tiffany, understand? Najana, understand? Okay. Yeah, can I give you a minute to jot down whatever you need? Then we move on to the next part. So you can see that from here, the magnets and the compass actually go in one round, going away from north, going towards the south. And the magnetic field lines, same thing, going from north to south. Okay, nothing much here. I remember there's one thing that I need to talk to you about is this north signal pole. Come to that later. Okay, so there's no issue. 10 seconds, let's sort out question 1A. Question 2, I think no need to do now. It's like all cut and paste from the one in front. We don't waste time doing this. Give your 10 seconds, sort out your question 1. How would your compass needle point? Oh yeah, I forgot to update your last year's batch result. Of concern for you is the pure physics. Pure physics for my last year's batch. One person got B3. This is out of a total number of about 8. So one person B3, and then for the A's is half lor. I think it's 3A1 4B3 for the pure physics. For pure chem, there are 7 people total. Also 1 B3. And I think something like 3 2s and 3 1s, something like that. Then combined physics and chem is, yeah, everyone is distinction. So, okay, statistically, both of your school students should be at least a A2 eventually. Whether you all can, don't make careless mistake, don't screw up practical. That's the difference between your 1 and 2. Okay, let's take a look at this. So you should have something like this. Moving away from north, going into south. So the field line should, the arrows should look like this. Okay, any questions? Okay, so you can see that when there's one thing to talk about, I want to talk about the north-seeking pole thing. So we have north and south. So you can see that if the magnetic field goes this way, you can see that the magnetic field is heading to south. So I got my compass pointing towards this side. Okay. So if you're fully understood this, okay, the direction of the compass needle. Now let's take a look at if this is planet Earth. Okay, and over here is the equator. Okay. Let's say where I'm standing, right? Let's say I'm holding my compass. My compass goes this way. Okay, we know that this is the North Pole. This is the South Pole. Based on your understanding of this, Sanjana, do you think if I were to take the compass points to that direction, and I walk in the same direction where the compass points to, my question for you is, will I reach the North Pole or the South Pole? Assuming your starting point is at the equator, and understanding the concept of magnetic field direction, how the field line should look like and everything, if I were to walk in that direction, will I land up, eventually when I move in this direction, I land up in this place. Is this place the North Pole or the South Pole? If only you think about it also, and then we verify each other, see what you all think. Maybe both of you think about it. Let me know where do you think he's heading to. He's heading to the North or the South Pole. Once ready, let me know, both of you. So Jonah, I feel it's North Pole. Tiffany, do you think it's North Pole? Tiffany, you think it's South Pole? Okay. Can I make a guess why do you all think is it North and South? So, Sanjana, you mentioned that you're going to the North Pole. Is it because you understand your understanding is that when the compass point north, I follow, I must reach north. So in a sense, I will reach North Pole eventually if I follow the direction of the compass, because compass points to north means I go North Pole. Is that your logic? Yeah, Sanjana, is that your logic? It follows the compass needle. So the compass points to north means I'm going to the north. I'm going to the North Pole. That's the logic behind saying that you'll reach north. Okay, you mentioned about the compass aligned with the magnetic field. Okay, I think that's the reason why Tiffany chose south. Tiffany, you are going for this logic, right? That means you are walking this way. So you keep walking this way, then you reach south already. Is that the reason why you chose that? Because based on magnetic field, the compass needle should be like this, right? So the pole should be North Pole, South Pole, because the magnetic field line move from north to south. So by right, then does it mean that this is the South Pole? Okay, I think that was your logic. So Sanjana, do you think we'll reach the South Pole then? Since we say that the compass needle should follow the Earth's magnetic field, do you think we'll reach south then? Based on this logic. Do you think so? Going by the logic of aligning with the Earth's magnetic field. You mentioned about reaching the South Pole. Both of you is right and wrong at the same time. First of all, if let's say right, my compass needle looks like this. It goes like this. That means the Earth's magnetic field, right, should be this way. Let me draw a hidden magnet over here. So that means the Earth's magnetic field, for it to be correct, it needs to be south, north, and then the magnetic field will go this way. Following the Earth's magnetic field, the compass will point this way. Sanjana, do you agree with this field drawing? Tiffany, do you agree? Yeah, strictly based on magnetic field lines, the magnet should look like this, which means, right, your concepts are not wrong. It's the way we define the polarity that is confusing. The red line here, this North Pole has another name. This North Pole is also known as magnetic South Pole. This South Pole is also known as magnetic North. So whenever we take the compass and we start walking, where are we heading to? We are really heading to the North Pole. And this North Pole is determined by geographers. So this is also known as geographic North Pole and geographic South Pole. So when you take your compass needle and it points north, and when you walk straight following the compass needle, you will reach the North Pole in that blue thing, the blue North Pole, and not the magnet. When normally we talk about North Pole and South Pole, we don't refer to the magnetic north or magnetic south. We are more dealing with the real geographic north and real geographic south pole. So as a result of the Earth's magnetic field, it will cause the compass to point upwards to the north, but the Earth's magnetic field, the north and the south, is not the same as the geographic north and south. They are inverse of each other. So that's the reason why when we take the compass needle, we follow the North Pole, we really will reach the North Pole. We follow the arrow, we reach the North Pole. But that North Pole is also known as the magnetic South Pole, which gives rise to the magnetic field that affects our magnets that will affect our compass in the so-called correct way. So compass needle pointing that direction will point us to north. That's the idea behind it. Can you help me jot this down? Sanjana, make sense? Tiffany, make sense? The geographic north-south is not the same as the magnetic north-south. Okay, Sanjana, I explain one more time. Let me draw a simple Earth. Do you agree this is what we understand by what North Pole is? This is what we understand by what South Pole is. Okay, so if we take our compass needle, our compass needle will point this way, and then you will reach the North Pole because the compass points to the north. Do you agree? Okay, let's talk about why is it pointing to the north based on the Earth's magnetic field. So for the compass to point to the north, the Earth's magnetic field needs to be like this, where it's north at the bottom, south at the top, so that it produces a magnetic field that goes like this, going down and then going up this way. So you can see that when the magnetic field goes up this way, the compass needle also point in the same way. So this south pole is also known as where the magnet is. This is the magnetic north. On top is also known as the magnetic south pole. In order to create the magnetic field that will point your needle towards the North Pole for you. The Earth's magnetic field is inverse of the actual North and South Pole. Does it make sense? Yeah, can you help me jot down whatever you need for this? So we are done with this revision portion. So next, we'll actually move on to this. So Tiffany, if you are done already, can you help me move to this topical? We finish up the MCQ first. Okay, Sanjana, you jot down whatever you need. Once you are done, please proceed to the MCQ. And if either or one of you is done with the MCQ, please let me know. The moment the second person finish, I'll give you the answer. Okay, let's sort this one out and then we look at the MCQs. All right, can you take a look at the MCQ answers and then any questions that you need me to go through, please sound out the question number. If you need anything. Okay. Let's look at question 8. Okay, question 8 is okay, the choices to pick, first of all, these two is out because they are non-magnetic material. Now, if you all got it wrong, you all probably choose iron. But do remember, iron is a soft magnetic material. And its property is that it is unable to retain magnetism. And because it's unable to retain magnetism, your plotting compass needle, the needle is technically a permanent magnet. And you need it to be a permanent magnet in order for it to interact with the Earth's magnetic field. So you can't choose iron because iron wouldn't have Earth's magnetic field. In order for it to work, you need to have a permanent magnet over there. So this thing here is your hard magnetic material. This is the one that is used for permanent. And because it is able to retain magnetism. Okay, so that's why the answer should be Brazil. Canada is wrong. Okay, any other questions for this? Okay, Tiffany, you need anything else? Okay, great. So, can we settle the 4 questions from section B? Yeah. Again, once you are done with the 4 questions from section B, let me know. Okay, question says two properties of magnet. There's a lot of properties that you can mention. So things like, for example, has a magnetic field. Able to repel another magnet. These are common answers that we can use. Similarity between magnet and permanent magnet. Electromagnet basically is the one that can switch it off by turning off the current. So same thing, you can actually state the same thing for this because they are all talking about magnetic materials and or rather properties of a magnet. Both of them will exhibit properties of a magnet. So we can talk about the same thing. Okay, and 2 differences. First off, just now we have seen is the material. For electromagnets, we need to use iron. Permanent magnets, we have to use steel. So first off, material difference. The second is, I will say, property difference. For the electromagnet, unable to retain magnetism. And this case is able to retain magnetism. Okay, the same thing. Or you can also say that this thing here can be easily magnetized. And not easily magnetized. Okay, you can go for any of these properties will do. Okay, let's look at question 2. So what this magnetic catalyst does is, for example, you use it to shut the door and things like that, right? So we're using magnetic poles to actually attract and induce all this. So let's go for straight processes before we deal with the last one, mechanical. So it says what happened to the soft iron when it's brought close to it. Tiffany, other than saying that the soft iron will be attracted, right? What else do you think you will want to say? What will happen to the piece of soft iron other than being attracted to it? What else do you think you'll want to say? Not fall off easily. Okay, before they can attract, something must happen to the soft iron material. what happens to it? And the result will be right. I will say that because this thing happens, and hence it will be attracted to the permanent magnet. So what actually happens to the soft iron material? What's the principle for attraction of magnetic materials? Let's go back to this. Remember about this nail thing? What's the process we talk about? How does the iron nails get attracted to the magnets? Induction, correct. The phrase that we want to use is induction. So we say the soft iron material is induced to become a magnet, and it will be attracted to the permanent magnet. The induction part good to what? Part B, why is soft iron used to instead of this? This is basically just this is a ferro. We'll say it's a ferro magnetic materials. And for aluminium, it's a non-ferro magnetic material. That's all. Okay, and the last one, mechanical catch versus magnetic catch. Okay, let me share a quick screen over here, what a mechanical catch looks like. Then Sanjana, can you explain why mechanical catch is not as good? The simplest. These are like magnetic catch. This is the ones that you can use to lock doors and things like that. So why do you think these sort of door catches are not as good as magnetic? Or rather, what kind of advantage does magnetic catches have over the mechanical ones? Both are used to lock doors, but why is this slightly inferior than the magnetic ones? Why do you feel magnetic is safer than this? No one talked to tell me about safety before. Your finger got snapped by this thing before. Your real life experience. I think nowadays you're growing up, though, you all don't see this very frequently, right? If it's not so much of safety, Tiffany, what do you think? Oh, not because of the magnetization and things like that. Okay, first of all, how these magnetic catches work, you can see that there's a little space here. So to lock the door, right, this diamond shaped thing has to squeeze through the roller. Actually, St. John, I mentioned about rusting. If I change this to stainless steel, then won't rust really. So the issue with all sorts of mechanical catches, regardless of whether it is able to will it rust or not, right? If you look at this part here, this part actually carries a spring. So when you take this part here and you squeeze it in, this roller will move apart to allow the very wide portion to squeeze in. And then you see this portion here is also like a same diamond shape here. So when this whole slot thing goes in, into this wheel will come back together and catch hold of this diamond thing in it. So this is like it physically grabbing hold of it. So that's how this mechanical catch works. It slots in, the roller move apart, and then it slides into the hole, and then the roller will snap back and hold it in place. So with a mechanic like this, it's actually pretty easy to use it as a door catch. So when the door comes in, they will just slot into the slot there. But comparing to a piece of magnet, where you just use two pieces of material to attract each other, right? This thing has a disadvantage. So hearing how this thing works, right? Do you all still have any other ideas? One last idea. Any idea why mechanical might not be as good as the magnet ones? Saying that this thing will squeeze in, open up the squeeze out the spring and then slot it in. So why is this not as good as a magnet one, a magnet version? What do you think? Think about when this thing squeezes in, the roller has to move apart, then snap back, move apart, snap back, move apart, snap back. What's going to happen when it keeps moving apart, snap back, moving apart, snap back? What do you think is likely to happen? Like keep opening and closing this door compared to a magnetic one, like maybe 50,000 times. What's likely to happen? Yeah. And Jana, your suggestion about less wear and tear, that's the one. Because these are all mechanical moving parts. As long as you have mechanical moving parts, you will have some element of friction. You will have some elements of wear and tear due to frictional forces between the roller and the diamond shaped catcher. And because your things like this uses spring, over many cycles of rolling away, the spring might become loose. The spring might become loose at the end of the day. So when the spring becomes loose at the end of the day, the door catcher doesn't catch on so well anymore. Whereas for a magnetic field, yes, over time your magnet will become weaker, but tends to be more durable, I would say, as compared to this physical catch, where there is physical wear and tear and degradation of all the physical catches, like all the springs get looser and things like that. Then the door will not close well. So I will put it down as anything that is somewhat like mechanical, right? Always will have this issue of having some form of wear and tear. Okay, so this is my answer. Okay, the first MC is a magnetic catch, reduces the damage. Okay, next, let's look at question number 3. So it says using 2 arrows. So draw the direction of the force acting on the north pole of magnet P. So in concern is this guy by each of the pole of magnet Q. So we want to know how all this interact with the north from P. So let's talk about the north and north. So what are the forces? The force that is acting on the north pole. So because they are like poles, you'll push it away. So my answer for A, which is in red, will go up this way. This is a repulsion force. So how will the north and the south pole interact? They are going to attract. So there will be a pulling force. So the south pole will pull the north pole towards it. So this is my second arrow. So this is called the forces acting on north. The north will repel the north away upwards. The south pole of Q, which is this, will attract the north pole. So you'll pull it in this way. The concept of like poles repel and like poles attract. Okay, that is for 3A. Yeah, please help me jot this down. Then we look at 3B together. So in blue will be my second question. Using two arrows, show the direction of the force acting on the like poles of Q and P. So the like poles is this pairing and then this pairing. So actually nothing much. I think it's just talking about acting on both poles. So they'll be repelled away. Quite a silly question. So for part C, I will say that as a result of all these forces pushing each other and things like that, right? The two pieces of magnets is likely to move further apart. And when they move further apart, reason will be just a simple like poles of a magnet repel. Okay, give you a bit of time. Can we look at this question 4? Okay, finish up question 4. 1A, what's defining magnetic field? I just write it down like just definition only. Okay, so this one very simply is just a region around a magnet where magnetic material experience a force. Okay, this is just definition. Okay, can you help me with question 4? And then for question 1B, describe a method. Okay, do not use stroking method. With another Sec 4 class, end up they go and draw the stroking method. Let's not draw the stroking method. The objective of this, right? Normally they don't want you to, the questions don't want you to do stroking. So find other ways to do it and see if you can also, right, include a diagram. Okay, can we sort out the last two questions for this? Well, later for 1B, once you are done with the drawing, can you all take a photo send to me? I want to see how you all draw this. Okay, but let's do question 4 first. The effects of a pole on others. This one is very simple, right? Like poles repel, unlike poles attract. That's all. Okay, so magnetic field lines, we have drawn this so much already. So do at least 2 rings on each side. And then you have the feelers in front, and then the tail behind. Magnetic field, always remember, always out of the north, going into south. So always heading towards the south pole. Okay, that's all. Part C, how do you use a plotting compass to show that what we draw in B is correct. Okay, so over here, a simple one we can say, place the compass around the magnet. Okay, the direction of the needle. In the compass should be the same. We'll say it will be the same as the magnetic field direction. Okay, that's all. So once you are done with your 1B drawing, and can you also give me simple description of what steps you want to do and some of the keywords? Then I will go through with you when you are done. Okay, so this one, on time, on target, when you are done, send it to me. So yeah, I want to see your drawing. Okay, so again, the plus and minus represents the polarity of the battery. The currents will flow out from the plus side. And then it will go something like this. So when you do your right hand grip rule, if your pencil is here, you will grip your fingers over it. All right, your fingers will be over it. It's a bad drawing, but following the current direction, then your thumb will point this way. So this side should be the north and south if the current is coming down. You understand that, Mr. Jonah? Alternatively, right, if let's say the current is the opposite direction, then the current will go this way, going up. And then when we do the right hand grip rule, then the north will be on this side. So when the current is going up on the side, you get something like this. Okay, these two directions, all right. If it's okay, I send you the write-up for that. Okay, let me send you this. You take a look. Does it make sense? Okay, I just WhatsApp to you.